Okay, in this video, we are looking at properties of periodic table, and we have certain properties of periodic table. We have atomic size or radius, we have ionic size or radius, we have ionization energy, we have electron affinity, electronegativity, melting and boiling point, heat, and electrical conductivity. So in this video, we are going to be discussing all of that. Okay, so let's start with the atomic size. Atomic size is the size of an atom, defined as the distance between the center of nucleus of adjacent atom of an element. Half of this distance is called atomic radius. So just like we see in the diagram, if you have two atoms like this placed on adjacent side, okay, the distance between their nucleus, like we see here, is called the atomic size. Now, if you divide that distance by 2, you get the atomic radius. Now, we use this definition because remember that an electron consists of a nucleus and an electron cloud surrounding it, But usually we cannot tell because the electron cloud can be distorted. We can't tell the size of an atom using the electron cloud because it keeps changing, it keeps being distorted. Okay, so that is why this definition is very relevant, since we know that the nucleus of an atom is fixed, and we can easily use that to define atomic size. Now, if you look at this statement here, it says that atomic size increases down the group but decreases across the period. So as we go down the group, atomic size is increasing, in the periodic table. But as we go across the period, the atomic size is reducing. So that's the diagram we see here. But let's see, we say that atomic size increases down the group due to increase in number of shells. Because as you grow down the group, the number of shells increases. Look at here, for period 1, they have 1 shell. Period 2 have 2 shells. Period 3 have 3 shells. Period 4 has 4 shells. So you see, as we are going down the group, the size keeps increasing because the number of shells are increasing down the group. But as we go across the period, the number of shells decreases across the period because of what we call nuclear charge, increase in nuclear charge across the period. Now, this nuclear charge, there is a calculation though, but I will not bother myself with the calculation. This nuclear charge increases when atomic number increases, and whenever there is increase in nuclear charge, the size gets smaller. Look at, for example, let's pick elements in the same period. Those elements, we have something like lithium, we have beryllium, we have boron, we have carbon, and so on and so forth. Lithium is 3, beryllium is 4, boron is 5, carbon is 6. So the atomic number, all of them have 2 shells. Lithium is 2, 1, beryllium is 2, 2, boron is 2, 3, carbon is 2, 4. They all have 2 shells. That means 2 shells, 1, 2, 1, 2, 1, 2, 1, 2. But as you go across the period, you see that the atomic number is reducing. Why? Because the nuclear charge is the attraction of electrons towards the nucleus. And once this attraction is much, let's say you have a nucleus here and you have an electron is attracted towards the nucleus. So once this attraction is much, it shrinks, because the electrons move towards the nucleus, it shrinks. And it is atomic number, as atomic number increases, that nuclear attraction increases, causing it to shrink, causing it to, reduce in size. So the reason why an element can be smaller, elements in the same period reduce in size as you go across the period, is because the nuclear charge increases. Once there is an increase in nuclear charge, the atomic size will reduce, will get smaller. Okay, so that means if I am comparing carbon and lithium, carbon has a smaller size than lithium. How do I know carbon has a smaller size than lithium? Even though they have the same number of shells, 2, 1, and this is 2, 5. But because this guy has more, the atomic number is bigger, is 6. They have the same number of shells. So anytime you are comparing two elements with the same number of shells, the one with the higher atomic number will have the smallest size. We have the smaller size, okay? But anytime you are comparing elements that are in the same group, obviously that is very obvious. The number of shells, like hydrogen, only one shell. I mean, for group 1 element, sodium, 2 shells, so it's bigger. Okay, sorry, after hydrogen, you have lithium, 2 shells, sodium, 3 shells, potassium, 4 shells, and so on and so forth. Okay? So here we see the nuclear charge is the attraction of valence electrons towards the nucleus or inward pull of electrons towards the nucleus. This quantity increases with atomic number. I think I've made that clear. Okay, so we now look at the ionic size. Now the ionic size is the size of an ion, but the variation of size depends on whether they are cations, anions, or isoelectronic ions. Okay, that is what we should note about ionic size. So let's move on here. Now we see a case 1. The size of a cation is smaller than that of its corresponding atom. The size of a cation is smaller than that of a corresponding atom. Let's say we have an element, sodium, for example. Now, sodium, the configuration is 281. Now, if it loses an electron, the configuration will now become 28, just 28. It has lost one electron. Okay. So first of all, how do I know this is sodium ion? So it should be Na plus. So you can see that sodium atom has a larger atomic size than sodium ion. Why? Because sodium atom has 3 shells, 1, 2, 3, but sodium ion has only 2 shells. So from the number of shells, it can be clear that sodium atom is larger in size than the cation. Or we can say that sodium ion has a smaller size than its corresponding atom. Now, another way you can use to explain this phenomenon is that whenever an atom loses electron, the nuclear charge increases. Anytime an atom loses electron, it increases the nuclear charge. And anytime nuclear charge increases, what happens to the size? The size reduces. The size gets smaller. Okay? So that is another way we can describe that. Now, case 2. The size of an anion is larger than the size of its corresponding atom. An anion is formed when an atom gains an electron. So when an atom gains an electron, the nuclear charge increases. And whenever nuclear charge increases, what happens? The size will increase. So that means chloride ion, for example, chlorine ion has a larger size than chlorine atom. And this is very, very, this is very, very important. Okay, this is very, very important. Okay, so we'll move to the next case 3. Is that for isoelectronic ions, atomic size decreases as atomic number increases. Isoelectric ions. Now, what are isoelectric ions? Isoelectric ions are ions with the same electronic configuration. And I'm going to explain that using certain examples. Look at oxygen, for example. We have oxygen, the atomic number is 8. Fluorine, atomic number is 9. Look at sodium, atomic number is 11. Magnesium, atomic number is 12. Now, if I should write their ions, their configuration, I think the configuration here is 2, 6. Here is 2, 7. Here is 2, 8, 1. Here is 2, 8, 2. Okay. Now, but if I want to write for their ions, for example, now oxygen ion O2 minus means it has gained 2 electrons. The configuration will simply be 2, 8. Look at fluoride ion 9 minus, it can gain 1 electron. The configuration is also 2, 8. Sodium should be Na plus, meaning it has lost 1 electron. The configuration is 2, 8. Magnesium is Mg2 plus. meaning it has lost 2 electrons. The configuration is also 2,8. It has lost 2. So have you noticed that oxygen ion, fluoride ion, sodium ion, magnesium ion, all of them have the same number of electrons, which is 2,8, 2,8, 2,8, or we can simply say they all have 10 electrons. Now, according to the statement I made earlier, that as the atomic number increases, the atomic size reduces. So that means oxygen ion is greater in size than fluoride ion. Fluoride ion is greater in size than sodium ion. Sodium ion is greater in size than magnesium ion. As the atomic number is increasing, the atomic size is reducing for isoelectronic ions. I want to believe that you understand this. So we'll move to the next one. The next one is ionization energy. So what is ionization energy? Ionization energy is the energy required to remove a valence electron from a gaseous atom. So to remove an electron from a gaseous atom, a valence electron from an atom, is what we call ionization energy, the energy required to do that. Okay, now we are going to look at factors that affect ionization energy, and the first one is nuclear charge. Now I want to say this, that nuclear charge, like we say, is the inward pull of electrons towards the nucleus, the attraction of electrons towards the nucleus. Now, as nuclear charge is high, it becomes difficult to remove electrons from the nucleus. So high nuclear charge means high ionization energy, because more difficult to remove electrons, but low nuclear charge means low ionization energy. And nuclear charge is the main reason why ionization energy, as we see later, ionization energy increases across the period. Remember that as we go across the period, the atomic number increases. And as the atomic number increases, nuclear charge also increases. And when nuclear charge, that means the attraction of electrons towards the nucleus increases. It becomes more difficult to remove electrons from them. So if you notice, let's see group shell 3, period 3. Look at sodium now. Sodium is 11, which is 281. Then look at chlorine. Chlorine is 17, which is 287. You can see. Now, it is easier to remove an electron from sodium, one electron from sodium, than it is to remove from. Okay, so sodium actually has low ionization energy, but chlorine has high ionization energy. So you see that as we go across the period, ionization energy actually does what? Increases. As we go across the period, ionization energy increases. Why does ionization energy increase across the period? Because of increase in nuclear charge. Okay, so we see another is the distance of valence electron from the nucleus. So I want to say this, that the farther an electron is from the nucleus, the more easy to remove the electron. Okay, so the farther a parent is from the child, the more easy it is to separate the child from the parent because of distance. That's the same thing here. And this is the reason why ionization energy reduces as you go down the group. Nuclear charge is the reason why ionization energy increases across the period, but distance of valence electron from the nucleus is a reason why ionization energy reduces as we go down the group. Take an example. Look at hydrogen, for example. Group 1 element. Hydrogen has one shell, so that means one electron and a nucleus at the center, then just one electron. Yeah, something like lithium. Lithium has two shells, so it has the nucleus inside here. The valence electron is somewhere out. You see, the gap keeps increasing. Look at sodium. Sodium is 11. 1, 2, 3. This is the nucleus here, and this is the electron here. It keeps going, so it's easier to knock off electron here. So as you go down the group, it keeps getting easier to remove an electron. That is why ionization energy reduces as you go down the group. Now, another factor that affects ionization energy is what we call shielding and screening effect. Now we have two types of shielding. We have two types of screening effect. We have primary screening and we have secondary screening. Note this. The primary screening is when the inner electrons screen the outer electrons from the effect of the nucleus. If I take sodium for example, the configuration of sodium 11 is 281. So if I'm to draw the diagram, we have 1, 2, 3. Now the first shell has 2 electrons, the second shell has 8 electrons, okay, while the third shell has 1 electron, and you have the nucleus inside here. Okay, now you can see that there are inner electrons, and this is the outermost electron. This one here is the outermost electron. Inner electrons are shielding the outer electron from the effect of the nucleus, and as this shielding effect keeps increasing, the ionization energy keeps getting lower. It becomes easier to remove valence electron, from that particular atom. Now, so the shielding of the outer electron by inner electrons is called primary screening effect. Now, but we also have a secondary screening effect. In this case now, is the repulsion between electrons in the same shell. So 2 electrons in the same shell can repel each other, reducing the effect of the nucleus actually also on each other due to that repulsion. Okay, so we have primary screening and we have secondary screening. Now, the screening and shielding effect is also another reason why ionization energy reduces as you get down the group. Because as you go down the group, the atomic size, the number of shell keeps increasing. And as the number of shell keeps increasing, the inner electrons are shielding the outer electrons from the effect of the nucleus. They are making sure that the nucleus does not really get, is not really affecting the outermost shell. So that is another reason. Now that now leads us to the next, which is stability of atom. Here we have our first 20 elements for a reason. Now it is known that elements that have stable electronic configuration have higher ionization energy than the element next to them in the periodic table. Now, from what we did before, from the first 3 factors that we saw earlier, we can conclude that generally speaking, ionization energy should increase across the period, but should decrease as you are going down the group. Ionization energy should increase across the period, but should decrease as we go down the group. Now, but there are few exceptions, which is what we are going to see here. Elements that have fully filled electrons, or fully filled orbitals, or half-filled orbitals are more stable than the element next to them, and so the ionization energy will be higher. And where do we see this exception? We see it between, let's say, beryllium and boron, magnesium and aluminium, nitrogen and oxygen, phosphorus and sulfur. Now look at, for example, beryllium. Beryllium is the 4th element. The configuration here is 1s2, 2s2. Have you seen that all the orbitals are completely filled up? So its ionization energy will be higher than that of boron. As a rule, boron is supposed to be higher than beryllium, but because beryllium is more stable due to fully filled orbital, beryllium is higher than boron. So if we draw a graph of electronic configuration, of ionization energy, watch, from hydrogen to helium, it increases. You see that? Now, as we continue, lithium, it reduces a little. From lithium to beryllium, it increases. From beryllium to boron, it reduces again. I didn't add the picture. I would have shown you. That's my bad. But we should note that when an atom have a half-filled orbital or fully filled orbital, it means that their configuration is stable. Look at nitrogen, for example. Nitrogen is the 7th element. The configuration is 1s2, 2s2, 2p3. p3 is half-filled orbital. p3 is half-filled orbital. So its configuration is far more stable than that of oxygen. So ionization energy of nitrogen is greater than that of oxygen, phosphorus is greater than that of sulfur, magnesium is greater than that of aluminum, beryllium is greater than that of boron. Why? Because their orbitals are either half-filled or fully filled, giving them stable configuration. Please take note of that. That is the only exception to the rule. Okay, so let's move on. Okay, so the next is here we look at first, second, and third ionization energy. The first ionization energy is the energy it takes to remove an electron from a neutral atom. To remove an electron from a neutral atom is the first. The second ionization energy is the energy it takes to remove an electron from a +1 ion. That means that the atom has already lost an electron. You are now removing the second. Okay. The third ionization energy is the energy it takes to remove from a +2 ion. So look at it. An element like sodium is 281, has only first ionization energy. But an element like magnesium is 282, has 2 ionization energy, has the first and second, because it has 2 valence electrons. So you will need to remove the first electron, then you will now need to remove the second electron. Okay? Then an element like aluminum, that's 13, is 283. So 3 electrons, you remove the first, second, and third. Now I want to bring something also to your notice here, and this is where this is the case that is very examinable, is that the second ionization energy is higher than the first ionization energy, obviously higher. Remember, we said that when an atom loses an electron, the nuclear charge increases. That means the nuclear attraction, the attraction of the electrons towards the nucleus increases. It becomes more difficult to remove the second one. Now, if we eventually remove the second one, the nuclear charge again increases, making it more difficult to remove the third one. So you can see that third ionization energy is higher than the first ionization energy. Second ionization energy is higher than the first ionization energy. The third ionization energy is higher than the second, and so on and so forth. Okay? That is very, very important for us to know. So that means E3 is definitely much higher than E2, and E2 is higher than E1. That's the variation of energies. That is very, very, very important for you to note. So if they ask you to compare the ionization energy between magnesium and sodium, you should know that magnesium has a much higher ionization energy because you are going to be removing 2 electrons. Sodium has a lower ionization energy. You're going to be removing just 1 electron. Aluminum is mad, 3 electrons. Then last, why you see that ionization energy increases as you go across the period. That is very important for us to know. Okay, so we'll go move to the next one, which is electron affinity. Now, what is electron affinity? Electron affinity is the energy released when a gaseous atom gains an electron. Okay, so when an atom gains an electron, energy is released. Now, it depends on atomic size and increases with decreasing atomic size. So, electron affinity depends on atomic size. Now, look at what we have here. Hence, electron affinity increases across the period but decreases down the group. Now, so the smaller the atomic size, put it this way, the higher the ionization energy. The larger the atomic size, the lower the electron affinity. The smaller the atomic size, the higher the electron affinity. The higher the atomic size, the lower the electron affinity. Okay, so if we can check the size, we can know which one has a higher electron affinity. Let's compare. Let me pick 2 random elements. Let's say carbon and nitrogen. Carbon is 6, nitrogen is 7. Okay, so based on this, both of them have the same number of shells, 2, 4. This is 2, 5, 2 shells. So that means this guy will be smaller in size, nitrogen, because as long as elements have the same number of shells, the higher the atomic number, the smaller the size. Don't forget. Okay, so he has a smaller size. Smaller size means he has a high high electron affinity. Electron affinity. Then this one has a lower electron affinity. So electron affinity depends on atomic size. That leads us to the next, electronegativity. Now, electronegativity is the tendency of an atom to gain electrons, the ability or tendency of an atom to gain electrons. And it also depends on atomic size, and it increases with decreasing atomic size. The same thing with electron affinity. So hence, electronegativity increases across the period but decreases down the group. Now, I would like to say this. Have you noticed that ionization energy, electron affinity, electronegativity, the three of them are reverse that of atomic size? So, atomic size decreases across the period. Atomic size decreases as we go atomic period. But these guys, what are they? Ionization energy, electron affinity, and electronegativity, all of them increase. Ionization energy, electron affinity, and electronegativity, they all increase across the period. Increase. So, and any quantity that increases across the period will decrease down the group, and so on and so forth. This is important for you to note. Now we move to the next. We have what we call the electronegativity difference. The electronegativity difference tells us the type of bond that is formed between elements in a compound. Now, let me note here that every element has its electronegativity value according to a man called Pauli. He assigned an electronegativity value to elements, and those electronegativity values can even help us tell us the kind of bond that can form between elements. Now, in this table here, we have bond type electronegativity difference. If the electronegativity difference is less than 0.4, it means that that bond is a pure covalent bond. If it is between 0.4 and 1.8, it is polar covalent. If it is greater than 1.8, it is ionic. Now, let me also state this, that in different occasions, in different sites, textbooks, you're going to be seeing different representations or different numbers, but basically this is it here. Now we move. Let's see a question. It says predict which of the following compounds are ionic and which are covalent based on the location of the constituent atoms in the periodic table. A is BF3. Now here I have BF3, that's between boron and fluorine. Here I have a periodic table that shows their electronegativity values. So let's see, we have boron fluoride. Look at boron here, 2.051. Then fluorine, look at fluorine here. Okay, so boron fluoride now, the difference here will be 4.193 minus 2.051. I think that is going to give us 2.142. Okay, this is obviously greater than 1.8. So the bond between boron and fluorine is an electrovalent bond. Okay, let's proceed. Let's see the next. We have manganese and oxygen. So let's see, manganese and oxygen. Manganese, where is manganese here? Can I find manganese? Okay, I can see manganese here. So obviously it's not put here. Let's look for another example. Let's see nitrogen and chlorine, NCl3. Let's see the bond there. Nitrogen is this. This is nitrogen, 3.066. Then chlorine is this, 2.689. So the difference is 3.066 minus 2.689. Now when we subtract that, this will be, sorry, this will be 7. 2 minus this 7. I'm not with calculator here, so there's 2. So 0.277. So this is actually a pure covalent bond because it is even less than 0.4. Okay, so let's see more examples. I will just do one more. You can do the rest and send to me. Sodium chloride. So let's look at sodium chloride here. This is sodium 0.869. This is chlorine 2.689. So 2.689 minus 0.869. Okay, here 0 is 2 is 8. Okay, that's giving me 1.820. So that means sodium chloride, the bond is ionic bond because it is greater than 1.8, and so on and so forth. Okay, so when you can be given two elements and you're asked to find the type of bond between the two elements, all you can just do is subtract their electronegativities values they'll be given you, and you find the type of bond. Okay, the rest of the questions, please just answer them and send them to me. I would like to see your answers. Now, there are other trends. We have melting and boiling points. For metals, melting and boiling point increases across the period but decreases down the group. But for non-metals, melting and boiling point decreases across the period but increases down the group. Okay. Then we have heat and electrical conductivity. Those two values decrease across the period. Don't forget that the left side of the periodic table are metals, the right side are non-metals. So obviously we should expect heat and electrical conductivity to decrease across the period but increase down the group. Okay, thank you very much. I would end the class here.